All right, so up next on the wave particle debate to do with the nature of light, we have interference. So I have the title is destructive interference, because that's the weirdest one, but constructive and destructive interference. So just as a reminder of what this means from grade 11, constructive interference would be if you have two pulses that are in the upward direction coming together, they'd combine to make a combined pulse that's added together, basically, right? So you've got, say, an amplitude A and an amplitude B. If you saw them side by side, put them together, you have an amplitude A plus B, right? So picture those two being added together there. And then the green one would just keep going and the red one would just keep going. So they overlap temporarily. This video shows that. So I have a square wave coming in from, I'm trying to remember which direction things are here. Size this. Just trying to go full size, and I'll pause it. You want to go full size for me? All right, I'll leave it as is. So you can see this sort of square wave or flat top wave, anyways, coming in from the left, and then from the right, there's just a little crest. Right? What you're going to see is the crest at some point in this area, and so it's going to add to that flat section. So I did that on purpose. Had a big flat topped disturbance and a curve, right? So if you watch as we go along, there's the there's that crest that's just simply added up with the rest of those. So I'll say all these are at amplitude of 1. Well, then this is the extra amplitude of 1 there, and a little bit less one to either side of it, and so on. Okay, so they're adding together. And then, of course, the crest keeps going, and the big square pulse keeps going. Watch it go. Keeps going, and the other one keeps going. All right, so that's constructive interference. Back to my slide here. This little computer applet or GIF or whatever you want to call it used to sort of work slow enough that it was sort of interesting to watch, but computers got upgraded or whatever, and apparently the frame rate's a little fast. Anyways, destructive interference. I just keep it in because it makes me laugh. So destructive interference would be if you had an upwards pulse, combining with a downward pulse, and you can picture how an up of 1 and a down of 1 would completely cancel out, and an up of a half and a down of a half would completely cancel out. So you get destructive interference. You get basically no wave at that spot. Now, this version, I didn't bother to try and do matching pulses because it's hard to get students to do the same matching pulses I do on the other side, things like that. But what I did do is I'll show that basically this negative pulse certainly takes away from the positive pulse, right? So in this one, I think you have a flat top wave coming in again. Pause this guy. All right, there we go. So just pausing there, we've got another flat top wave coming in from the right. This time I've got a downward crest. So it is going to say this is down 1. It's going to change this one to be down 1 when they're overlapping. And you'll see that right in this area, right? So instead of it being a flat, it's taking away. Okay, so amplitudes, obviously, with mechanical waves can add or subtract. Basically, they're adding vectorially, if you put it that way, right? Next step for this, to relate to all things that we've seen and we're going to talk about, we can have interference patterns. So if you have a point source sending out ripples, and this is representing a crest, this is representing a trough, so an upward wave and a downward wave, right? So as this thing's going up and down, it's making an up and then a down and an up and then a down and up, and that's just going out in 2 dimensions all around. If it's a sound wave, it'd be going in 3 dimensions all around. It's just a wave, right, being sent out. So if you have 2 of them side by side, you end up with spots where you have destructive interference and constructive interference. So this constructive interference, if these are sending out signals in phase, as you can see, they're both crests at first, then say at this spot here, a crest has had the same amount of distance to travel as this one, and so they arrive in phase, right? If these are sent out of phase, this one would have been a trough, right? And so it would have been a trough and a crest, and so it would have been destructive interference. Off to the side here, the crest gets here, and this one had farther to go, so the crest isn't there yet, so the previous trough is there. Basically, you can think of it as, so this is an area where you have destructive interference. So the way they all line up is you have they're not actually straight lines, they're actually hyperbolas, but in the close range, this diagram's not terribly wrong, right? It's an approximation, but they actually kind of form curves a little bit. But you have spots, you have these lines along which there is, yeah, you have these patterns where you have constructive and destructive interference. Okay, so those are interference patterns. Something we learn about, you learn about in grade 11 in the waves unit. You can even hear it in sound waves. I certainly do that with my grade 11 class. And then we go back to what we saw a couple days ago about, or a couple lessons ago, about the little bands you see here, light and dark bands there. That's an interference pattern, right? So the light is bending, just like this. It's traveling in different directions, and so based on the same analysis of one wave traveling farther than the other, they arrive in phase or out of phase, and literally just cancel each other out or add each other up, add up to each other or whatever, right? So where they cancel out, you get these dark spots. Okay, so that's what those little fringes are, the little bands, sometimes called fringes. Okay, it's an interference pattern with light. So we know a lot about how waves do it, and then we see light doing it. So obviously, more good evidence of wave nature of light. A demonstration of this, just another way to see patterns of interference of light. This is just a film canister, like a little, I don't know if you know what a film canister is even anymore. It's just a little container, a little round container, right? With a little cylinder. Anyways, the open end of it, you dip it in soap film, and then you let that soap film gradually fall down, right? Get drawn down by gravity. And so the top section gets super thin. Okay, this has been left long enough where there's actually still a film there. It's just so thin, we're not seeing it. Well, we're not seeing it because of destructive interference, and I'll show you why, the analysis as to why. This is a little video of what it looks like. That's a film canister, and then I just dipped it in some soap film, and soap make a little bubble on there, basically, right? And as this see the top section almost looks completely clear. It looks like there's nothing there, but there actually is still soap film there. And when I tap the container or the wind in the room, I should have blown on it a little bit or something. But basically, you see it move a little bit, right? Because there's a line there where the soap film is thick enough that you can see it. Here's it's thin enough that you can't see it. And again, we're going to analyze why and how that works. There's a picture of it. All right, so this is the thin film interference, okay? So explanation of this with a wave explanation, right? So we got this thin film that's super thin at the top and it bulges thicker at the bottom as the soap film collects at the bottom. So we're going to talk about a ray of light coming in, and actually we want to think of this more so as light coming straight in and bouncing straight out, but I draw it on an angle just to make it a lot easier to visualize. So light coming in reflects off of this soap film, right? Bounces it. So we want to look at the kind of reflection you have here. And there's also going to be some transmission. So we've talked about partial reflection, partial transmission in the past, right? So we're putting it all together. So the partial reflection is going to be like a fixed end reflection. And so that's going to be out of phase with the original light. And then you have light keep going through this partial reflection also, or partial transmission, sorry, also. So then it's going to reflect, but that is going to be, right, there's going to be a partial reflection on the back side of that film, soap film, that you're visualizing, sitting, where is it here? It reflects off the front edge and then reflects off the back edge. So off the back edge, it's a partial reflection off of essentially nothing, right? So that means that would be an in-phase, reflection. So that means that these guys end up out of phase with each other, okay? That out of the way. So the two rays end up joining back together. This is a very, very, very thin film, by the way. Okay, this is the top section. So the thickness is greatly exaggerated for clarity here, but I mean essentially this does not add any distance to the path, and so it's not contributing to any in phase or out of phase arrival, right? So because it's a super, super thin film, okay? It's really just the effect of the reflection phase change. So that means that they'd be arriving out of phase with each other, and so it's going to be dark. So that explains why the reflection from a really thin film is very dark. And they don't reflect light. the surface observed to be basically black, which in this case, because you can't see there's darkness inside of this black cylinder, we interpret that as nothing, because if there was nothing there, it would look black also. Okay, so that is the super thin film analysis. So why it's dark at the top. So that black, again, partial reflection off the first surface, canceling with the partial transmission, and then partial reflection off of that back side of the film. Okay, so it ends up with no reflection there. Okay, so the idea is you've got an in phase and an out of phase, or right, then you're getting a destructive interference. More pictures of the kind of thing here as it settles, right? The thin enough sections gets big enough you can see it, and eventually, apparently, the whole thing. I've never left it that long or had it last that long. The bubble typically pops at some point. An even stranger aspect of this, right? So it's kind of weird enough, but since the reflected light cancels out, right? There's no reflection, right? So then the question would be like, well, where does the light go? If there's no reflection, then what happens? Well, it turns out that the light can't reflect, so instead it goes through, which is kind of bizarre. There's I suppose there could have been other options, right? Same with total internal reflection. Like instead of it reflecting because it ran out of room to refract, it could have like absorbed in the material and heated up the material or something. This could have been like that too, I suppose. But this is just what's observed. Where we observe that since it can't reflect, instead it goes through. Okay, so with lenses, more light transmits through when there isn't than when there isn't a thin film coating. So we're going to see thin film coatings on lenses soon and analyze this out. Okay, but right now there's tons of light getting through this section. Okay, because it's not reflecting. So the what do I need here? Basically the same stuff. Oh, this is kind of an analysis of this as to why it's not super magical. It seems kind of weird, right? That it goes through instead. This kind of helps us feel better about it, maybe. Picture another partial reflection here, and then goes out and goes partial transmission. So these guys are going to end up in phase, right, with each other. So because these are in phase with each other, because it was out of phase, but then it's out of phase again. So it ends up back in phase. So these two are going to be in phase with each other. There's going to be constructive interference, and so it's going to be bright, right? So we can certainly justify why bright light is going to get through the other side, right? Yeah, so destructive interference, yeah, that's a wave property. Yet another piece of evidence, right, in support of wave properties of light. So some more details here, thin film interference details here, again, viewing at 90 degrees, right? If we had a quarter wavelength thickness, then we'd have the in phase and out of phase from the reflections like before, but then this would add an extra half of a phase shift. Remember, when we're looking at phase shifts, let me draw a little wave here for us. And then one just like it, which I'll do by cloning. Right? And so right now on here, let's say this, I'll have to group these together in a second, bear with me here, but let's go from top to top, because that's a full wavelength, obviously, right? Top to top, full wavelength. And then a half of a wavelength would only be half of that much to this trough part here, right? I'm drawing with my mouse, so forgive me here. So if I took this thing, let's group that together, and I move this a full wavelength, then we're still in phase, right? If I move it a half a wavelength, this is a half wavelength here, then they end up out of phase, okay? So basically the idea is, because this ray of light travels down a quarter of wavelength and another quarter of a wavelength, and remember, if we're viewing straight up and down, it's literally just a quarter and a quarter. That means we have this extra half out of phase. And so out of phase, but then out of phase again, these end up in phase, right? So if we have a quarter wavelength thickness film, then these guys would constructively interfere. So whatever color of light this wavelength corresponds to is going to lead to a strong reflection of that color, right? So yeah, so this part here, so wavelength of that color would be seen well. If it's red, it's going to look, if it happens to be red light, where this is a quarter of wavelength of red light, the reflection is going to look red. And, so this is where the colors come from. This is just a film, right? This is just a film of oil or whatever, and the thin film itself. This is a little different because I suppose it's oil on water, so there's a little more analysis as to whether or not there's in phase or out of phase reflections and so on. But the pretty colors kind of make sense, right? We're going to have spots where there's going to be constructive interference of red and constructive interference of green, and so that you end up with these reflections and purples and blues and oranges and so on. Okay, so yeah, if we had a half a wavelength thickness, then we'd be back to a full wavelength shift, and we'd only have the original out of phase stuff, right? So we'd be back to a dark reflection here, right? So we would have reflections canceling out. So again, because reflections cancel out, more light gets through, right? So we'll get to that soon here. Yeah, pattern of bright and dark bands. So at all these different thicknesses, we have spots where green light is constructively interfering as on reflection, and so on and so on. With all these different, so it's just a continual change of the thickness, which is causing those bands. So yeah, the use of this, yeah, you can really see, like, I shine light on this film canister, and you can see into the bottom, like there's nothing there, right? So you can see through really well. Whereas here you can't see the inside of the canister, because instead you're seeing the light that's reflecting off of it. So yeah, you can see through better for sure. There aren't any reflections. So the obvious application here is anti-reflection coatings on glasses, and we'll analyze why they work. Okay, but this one has an anti-reflection coating. This one does not. Which ones do you want to wear? Right? Much nicer to look through this. Glasses typically come with rear anti-reflection coating as well. So I'm looking through my glasses right now at the screen. There's windows behind me. I'm not seeing any major reflection from the inside of my lenses because there's an anti-reflection coating. So we have the lens, we have the coating, and you have light bouncing off, and so you're going to have a reflection off here and a reflection off there. So these are, I think, typically both going to be out of phase, I think. Let's see here. Depends on the refractive indexes of these things, right? So yeah, these are both fixed and reflection. So these are both going to be out of phase, right? So this one's out, this one's out as well. And so basically they're in phase with each other is what that's supposed to be showing, okay? And then we have quarter wavelength additions here. If this is a quarter wavelength thick, so we have an extra half, and so they end up out of phase. So we're canceling out that reflection, and that allows light to go through, right? Well, how it turns out is you pick a particular color that is going to reflect, and everything else goes through, if that makes sense, right? So if you're reflecting the red, that means by definition the opposite of it. You're allowing the blue and green, which is the higher energy stuff, to go through. So you'll see this tint on the coatings of lenses, and that's anti-reflection coatings. Okay, so they fine tune it, they engineer it specifically to get rid of a particular shade of light that you're not going to notice as a problem, and it increases optical clarity. It increases the amount of light that comes through. Okay. So this is just showing the idea of all the different wavelengths, right? If it happens to be a quarter wavelength of red, then red reflects. A quarter wavelength of yellow, yellow reflects, and so on. You see all the different colors. So what do we have here? We have a question where we have summer months, amount of solar energy entering a house should be minimized. And so they're talking about putting a coating on glass to reduce the amount of light that's transmitted in. Okay, we're trying to minimize transmission. So they should have said as part of this that this coating is in between the refractive indexes. That's the analysis I'm going to base this on. So you'd have an out of phase reflection off of here, and then another out of phase reflection from there. And so if this was a super thin coating, by definition, we'd have no reflection, and so light would go through like crazy, the opposite of what we want, right? And so you want to set it up so that the path difference here does not need to change the phase. What am I saying here? Yeah, they're both out of phase. Gotta get my head straight here. Reflection, this will maximize reflection already. Yeah, because because they're both out of phase with the original. So they're in phase with each other, and so we're maximizing reflection as well. I think I might have said it wrong a second ago. I apologize. So if we had a total path of wavelength or 2 wavelengths or something like that, that'd be fine because we wouldn't be changing the phase, right? So that means that half and half has to add up to a whole or a 2 or whatever. And so a nice thin thickness would be a half wavelength. If you can make a thickness a half a wavelength of your thinnest coating, other than so thin that it doesn't contribute anything, I suppose, which might be engineering-wise impossible to do. So if you can get a 0.5 wavelength coating, that's going to maximize reflection and therefore minimize transmission, reducing the amount of heat that gets into your room. Okay, so that's what this was here. So to get the actual value, you use the index of refraction, you use the part of Snell's law to do with the wavelengths, and you end up calculating the thickness the coating needs to be, the wavelength of the light in the coating. So that is, so then the thickness is half of that. And so kind of some old news there of calculating wavelengths based on indexes of refraction and so on. And another application of this, CD players and DVD players, not as common in use anymore, but you might have heard of them or seen them. But you have light laser coming in, bouncing off of this surface, and then a laser coming in and bouncing off of that surface. And they're so close together, these arrive together. And so you can see if this was a quarter wavelength, these would end up out of phase from each other. And so that would be an instant in time when these are canceling. And so it would be a dark, the sensor's not getting light. And then here it is getting light. And so basically the sensor's getting light and not getting light, just basically on, off, or ones and zeros, which is, of course, what digital is, right? Your favorite song in your phone at the root level is really just a bunch of zeros and ones, binary code, right? So it's a microscopic view of the surface of a DVD there. Interference pattern in wedges. This isn't a ton different. This is basically the same as the soap film, but you look at, it's just slightly changes the types of reflections. So here you'd have a free end reflection there and a fixed end reflection there, right? So this one would be no phase change from the original, so in phase we call it. This is a reflection off of a slower velocity, so like a fixed end, so it'd be out of phase. And so, if this gap is really thin, these are going to be out of phase with each other. And so it would be a dark, there'd be no reflection. And then based on the thicknesses, if we add in a phase change, right, we have spots between wedges of air wedges where you'd have these bands of dark and light, right? This, you might even see this if you just have like two sheets of glass just sitting together, and you press on one way or the other, and one spot or another. If there happens to be a little dust particle in one edge, there'd be a little wedge of air in there. And so you can actually see the little bands like that. You may have noticed that at some point in your life and wondered why. And this is the analysis as to why there is little bands of light, right? In order to be able to do work with this, a little bit of math kicks in here. And so we've got similar triangles here. And so, because they share an angle, it's basically the angle similarity, right, from math class. So if you look at this distance over the entire distance, so little triangle over biggest triangle, we have the little thickness of the wedge here over the thickness at the edge. We'd have a little similar triangle action going on, and so that you could solve out and so on for numbers. Similarly, with another location, we have the wavelength in comparison to L, right? So that wavelength in comparison to L, or x2, x2 and L, and wavelength, full wavelength instead of half wavelength in comparison to the thickness over here. So we've got these measurements, things that we know make sense based on the geometry. So the x1, these are spots where there'd be dark fringes, right? As we analyzed on the previous page. And so with the dark fringes, you can measure the distance between the dark fringes pretty accurately, because you can count out 20 fringes, measure the whole distance and divide by 20, right? You can get some pretty accurate measurements there. So that's x1 minus x2, which is this, which algebraically becomes this, right? So basically you can measure the fringe spacing. You can measure the length of the whole length of the wedge. You can know the wavelength of light. If you're shining red light, you just look up what the wavelength of red light is, and then you'd have this thickness T. So depending on what if you know the thickness, you can figure out what the spacings would be. To me, the more interesting option, unfortunately, my example is the opposite way, because from the resource where I got it from. But to me, if you measured the spacing and the wavelength, and you're using a particular color light, you can measure the length. You can actually measure super, super, super small thicknesses with this. So it can be used as a measuring tool. Kind of neat. right? So this example, one of these here, yeah, this is one where they give you, I think, the thickness. Like you've got a piece of paper with a certain thickness at the edge. Is that right? Yeah, by thickness of paper. So they gave the thickness, which I'm thinking, okay, how do you know that, right? Instead, I would think of it as we measure the fringes, fringe spacing, and then be able to say, oh, we measured the thickness of this tiny sheet of tissue paper or something. That would make, more practical sense as to how this would be done, but textbooks aren't always as on focus with practicality. But I just want to mention that because that's good to know. Anyways, yeah, plug numbers in. Get what the fringe spacing would be. So this would allow you to predict, like if you put a known thickness in a wedge, you'd be able to predict the thickness or the distance between fringes. This is just an analysis as to what, if the air were replaced by water, so you'd have different wavelength values. It just would change the spacing, but again, not a super practical version of this or use of this. So the next slides I just left in because it's just another version of the information. If you feel like going through it, it's just different look and feel to it, but same information for the parts that it doubles up on. And that's it for now. So there's your practice assignment. And yeah, thanks for watching and let me know if you have any questions.